Hello, welcome back to Learn It from a Layman. I'm Carl Christensen, back with Matt, and it's just us tonight. I think it's the first one that we've done just you and me, right, Matt?
I don't know. Maybe. Yes. Yes, it is.
I think
It's
so.
an exclusive feature.
That's right. This one's going to top the charts, I'm sure. Today we're going to be talking about machine learning, a little bit of artificial intelligence and robotics mixed in with the, but just, yeah, the basics of machine learning and AI. So I have, my background in this is limited to natural language processing, which is like a subfield of machine learning, which is essentially just language related machine learning tasks. And I'll talk, those are going to be all my examples essentially. Matt, do you have any like real world usage of these? I don't know if you ever talked about these in any of your classes.
Not particularly, no.
Okay.
My field of work focuses on actual intelligence rather than artificial intelligence.
Hey, they're getting close to each other.
Uh,
Um, okay, well, let's first for the layman kind of make these terms a little bit less scary, because machine learning and artificial intelligence, you start thinking about, well, I mean, obviously jump to movies like iRobot or, all a variety of robot movies where the robots are taking over the world, or Skynet, or whatever Shia LaBeouf was in.
that would be Transformers.
Here's another one where a computer becomes like self-aware and
Yeah, Transformers. That's Optimus Prime, the machine that has learned.
that's not the one I was talking about, but I don't remember the name of it. It might Sky. I don't remember. Anyway, the that's not specifically what we're going to talk about. That maybe at the end we'll talk a little bit about Ray Kurzweil and some of his predictions. But generally, machine learning is specifically just a task that you can use calculations for that can help create a model essentially of a particular, well, so I guess the best way to do it is give an example. So an example of machine learning is classifying a set of documents as to what their genre is, right? So if I've got a bunch of documents there that are either about nature or war or home improvement, or let's say it's just those three topics, and I want to be able to say I want to go read through 100,000 documents. Well, that's going to be too big for a human to go do that. It seems like a very easy task for a human, but now we're talking scaling it to the point where it's no longer something that a human, it would have to be a team of humans. Anyway, the man hours become intractable. And this is a very basic example. Machine learning can also go all the way to the end of the spectrum of where something, you're trying to essentially detect something and classify something that humans can't really do. And I'll give another example of that later. But in this basic example, you have these three different categories, and you want a computer to learn, a machine to learn, that's the machine learning, how to identify these different documents as belonging to these particular classes. And so you have to give it some data, and that's one of the big things in machine learning is the data. Not like the Star Trek data, but the
clarification. But yeah, I mean, to summarize, when we're talking about machine learning, we're talking about training a computer essentially to make a decision based on data, whether it be to tag it as a this or a that, a red, yellow, or blue, or to react in some way or other. You're basically training a computer to look at a thing and make an appropriate reaction.
Right. And that's what the model is for. So essentially you give it this, what we refer to as training data. So just a bunch of already labeled data. So let's say you have 1,000 documents that you've already.
If I could jump in,
yeah, sure.
Something that I might suggest that you do before we go much further is lay out kind of a structure of how we're going to talk about the topic. We're kind of defining what machine learning is, but then lay out the structure of we're going to define it. Then we're going to talk about how you'd go about doing it, all the different parts, some definitions, all that kind of stuff. It might be good to just map that out beforehand, especially for me, because I don't know.
Well, yeah. So just to finish the explanation here of machine learning, but then I do want to, I guess, just high level discuss what machine learning is for the layman versus artificial intelligence versus potentially robotics. And then we'll dig into more of what there are lots of different ways to do machine learning, right? And so we're going to talk about some examples of that, the way that they model it, the way that we calculate it, and there's a lot to talk about there. And so we'll hit on some of those. And there's something called supervised learning versus unsupervised learning. We'll just discuss kind of what the difference is and some of the examples of those, and then we'll have some real world examples of where machine learning is useful and what some of the ways that we kind of interact with it in a day-to-day. And then we'll move on to artificial intelligence, something, and I'm not as familiar with, but I am familiar with something called cognitive modeling, which does have some relationship to artificial intelligence. So we'll talk about that briefly, and then we'll move on lastly to kind of robotics and the future of being able to, have your own, robot that you can go have do jobs for you. So, but yeah, so machine learning, 3 topics, or three categories, bunch of documents. You've got training data, which is just labeled data. So I've got 1,000 documents, and all of them are labeled for these different classes. What I say, war, nature, and home improvement, right?
For example, yes.
For example, exactly. And now I need to train my machine and we'll discuss how you do that. But at a high level, I'm just going to, this data, these 1,000 documents, and with these 3 different classifications already put on them, is now going to be fed to the computer. It's going to learn from those documents, and then you can give it the rest of the 100,000 and have it label the rest of them. Now it's going to have there's going to be a degree to which it is accurate, and you can figure that out. So essentially, based on your training data, you can figure out how accurately am I going to be able to label all these documents and put them into these 3 classes. Because let's say you take 90% of your training data and train your model, and your model once again is just your decision probabilities. So you're teaching that machine to take all of this data, and now it's going to make this model that's going to tell it, okay, I've got this new document, I'm going to look at it, and based on my model, I'm going to say, oh, it's this type. So let's say 90% of your training data, you give it to create this model, you use the last 10% to test it, so that you can say how accurate is this machine, how accurately has it learned to label this data. And so you can test it on that last 10% and then calculate, oh, it's 95% accurate. And that gives you an idea of how good it's going to be across the whole data set, obviously. So that's at a high level what machine learning does. A very simple task there, but that's the idea behind machine learning. Is just a task that you can feed it data, and then it will create something that will help make decisions to do a particular task. So that's machine learning. Artificial intelligence is at least 1, if not 2 levels further than that. It's essentially taking machine learning, putting it into a kind of a structure of being able to make decisions and employ particular machine learning parts together, or just being able to make decisions independent of particular models that it already has. So artificial intelligence is more fuzzy, nebulous, at least in my mind, as far as being able to say, I need to be able to do this thing and this thing and this thing and this thing, multiple tasks, unknown data coming in, and being able to make decisions and correct judgments based on what it's seeing. So there's a whole infrastructure there. It's a little bit more, one of my teachers called this type of thing, I think his term was black magic, or so this, you're getting more towards the edge of hard science and a little bit more of you know, trying to create something that is not a voodoo doll, but a little bit more approaching human intelligence. That's the idea of behind artificial intelligence, obviously, being able to take something and do something novel with it. Does that make sense, Matt?
Yes, it does. When you say approaching human intelligence, I think that's a key. And like you kind of listed out the examples, but one of the reasons that you would, just in general, that you would do something involving machine learning or artificial intelligence or anything is to try to simulate the pattern recognition that humans are naturally good at. Humans recognize patterns and make decisions really well. We can very quickly look at a document and go, yeah, this is a document about war, or no, this is a document about whatever else. But yeah, training a machine to make that distinction is where machine learning and AI come into play. And there's something where you're always going to approach human intelligence. And I think that's kind of a key. So I'm glad that you said that.
Yeah, and we're going to hit on cognitive modeling, I think, more at the end. And cognitive modeling is the idea of so with artificial intelligence, we're just trying to take what the computer's abilities are and maximize them or solve an enigma. And essentially, we don't even know what we're trying to solve. We're just trying to make the best, smartest thing that we can. Cognitive modeling is more like we know what humans are capable of in a lot of different circumstances. Let's see if we can make a computer do the exact same thing in the exact same circumstances. And so you can see how that's a little different than artificial intelligence. In artificial intelligence, you can imagine I can take all these different machine learning algorithms. I can do things with them that humans wouldn't be able to do. So I'm not trying to exactly model a computer, model a human in artificial intelligence per se, or in cognitive modeling, that is the idea. I'm trying to model human cognition. And so we'll talk a little bit more about that later, but that's the kind of the difference there. And then from artificial intelligence, you take that step into robotics. So artificial intelligence can be, still located directly on a computer. I'm trying to make decisions and novel data, potentially using machine learning, but at least some structure that's going to take an unknown input and do something with it based on some algorithm or some, hocus pocus.
Hocus pocus is that's in your 400 level computer science courses.
Well, I was actually in the 400 level when this. I think that's what my professor, who now I believe he's a high level engineer in Zillow. He worked for Microsoft for a while as well. Anyway, but
we were talking layman cred.
Yeah. He was talking about specifically chatbots in that case, which is largely artificial intelligence. You're trying to essentially create a human conversation with unknown inputs. So essentially, I can type whatever I want, and you, as a computer, needs to be able to react to it in a way that is intelligent.
Sure.
So that's I think I don't remember if he said black magic or whatever else, but and that's kind of the idea behind some artificial intelligence is what's the best way to move forward. Anyway, but robotics is taking, you don't have to be artificially intelligent and or have machine learning in order to be a robot. Robots can do lots of different things, right? Usually these days, robots have some machine learning involved, but your Roomba or whatever it is that goes around and vacuums your floor, there's not a lot of software on there doing a lot of intelligent things, right? It's got a couple preset things, programs in there that tell it when to launch, the smart ones can map out and follow a path, but that's a far cry from artificially intelligent and being able to say, oh, there was a spill, let's go vacuum it up. So robotics can just be about taking computer software and mapping it into kind of more mechanical engineering and physics and data, or not data, sorry, and just the actual physical movement of a robot. So if you want to then take artificial intelligence and machine learning and apply that to a robot, then you have I think I don't know, a couple months ago we saw at MIT they had those human-looking robots that were doing like this obstacle course and jumping around. Did you see that, Matt?
No, I missed that one, but it sounds awesome.
It was pretty cool. They had they gave these robot-looking things, this obstacle course where they're essentially doing parkour, where they're jumping around, doing backflips, and it looked really cool. And then you see the outtakes, and you think, oh, it's still got a bit of a ways to go, because sometimes it messes up in ways that humans don't mess up. Even though a lot of humans can't do what you saw on that video where they were, like I said, the robots were doing backflips off boxes and all kinds of stuff. So that's robotics plus some artificial intelligence, being able to recognize objects and know how to take that object and apply an algorithm to it that will allow this metal to move intelligently. Not metal, obviously, a lot of it's going to be plastic, but anyway. Robotics is another field that I think people often confuse with machine learning and artificial intelligence, but they can certainly all be applied together, but they don't necessarily all have to go together. Okay, that's the high level of all those three topics. Let's dig in a little bit and talk some hard science, some math, some particular algorithms that you use in machine learning. Before I do, Matt, any questions?
No, not at this point.
Okay, so with machine learning, like I said, my experience has been in natural language processing, and so all my examples are going to come from that. But you've got this. Hopefully, these generalize across all the different fields of machine learning that machine learning is applied to. But what you do certainly have in machine learning is a difference between supervised learning and unsupervised learning, and we're going to talk a little bit about both here, but supervised learning, the idea is essentially you've got a human in the loop. You've got labeled data, and you've got a human essentially trying to curate the data and the model, and essentially you've got a very defined task that you're trying to accomplish, and that is what you use the data for. So, and those are often classification models, and so let me give a couple examples here. So with the first example, the very basic example I gave was an example of machine learning, a supervised machine learning algorithm. So essentially you've got data, and then you've got the set of unlabeled data that you want to use it on. In supervised learning, you've got a feature set. And so that is what I kind of glossed over at the beginning when I was trying to just get the high level. But when I've got these three classes that I'm trying to assign these documents to, the computer's got to learn how to assign these different documents to a particular class. And the way you do that is creating what we call features, which are essentially particular parts of these documents, and obviously, and you can imagine in the case of especially words, we're talking. In the case of documents, we're talking words, and some of these other cases where we can talk about syntax, parsing. In that case, we're talking parts of speech, those types of things. But all of these have these different parts of the document or parts of the data that can be assigned particular weight and how important they are in helping come up with the actual classification that you're trying to put on this object. So I've got this document, I don't know what it is, and so as a human, I'm going to read it, right? And as I'm reading, I'm picking out words, and if I read the word hammer and wood and nail, and I'm going to start thinking, oh, this is very likely a home improvement type of document, right? If I read the word plane and bomb, and oh, that's a war document. So you can see that there are particular words that have a lot of meaning in how I classify a particular document. There are words that are not useful, right? That's something we call as a stop word. We essentially just chuck it. It's not useful. But there are words that are just less meaningful. If I said the word wood, well, it could be in nature, or that could be home improvement, right? So that the feature weight, so the amount of information I'm getting from that feature, that word in that document is not going to tell me enough individually in order to be able to label that document. So the computer's got to be able to take all of this data in and figure out what is the best way to use these features to label it in a very accurate way. So with supervised learning, I'm helping the computer. Essentially, I'm saying, here's a document, you want to break it all into words, and here's how you do that. And once you have all the words, count the words, and then assign probability to the words given the topic that I've got the label on. And so that's how you build this model. There's a bunch of different ways to essentially assign the probability to these different features. Lots of different models and algorithms. A few of the ones
can I ask a question about features?
Yeah, sure.
So we talked about like words being a feature of a document. I'm sure many of us have, when we try to log in and you've forgotten your password, the little service that you're trying to log into starts showing you pictures and says, choose all the pictures that have a school bus or a crosswalk or a thing like that. Is that the sort of type of training data that you're, or like feature data that you're looking for?
Yeah.
Like,
So,
for a picture of a street, if it has horizontal or like white bars,
right.
this is probably a crosswalk.
Right. Yes.
And
Yeah.
when we're doing that, we're really helping define data for machines to train on.
That is largely true. Yes. Yeah, for sure. And that's that is true, and that's in the image realm that I only became a little bit exposed to in college. But yes, for sure. And you're right, because you can imagine same type of thing. You've got a picture, and the computer's trying to look at pixel information, and it's like, what do I do with this? And so it can kind of group things, and then it needs to know, well, is this group meaningful? I've got this group of white pixels. What does that mean? And so, yeah, that's you're teaching it. Okay, these groups of white pixels that in these situations can be labeled as a crosswalk, and so you're giving it data to train on. Exactly. So a few of these different models that they use to create these classifiers, these things that the machine learning algorithm uses to create these classes, to label these documents or whatever else. One of the ones that you learn first in any kind of class in computer science is naive Bayes, or a naive Bayes classifier. And that,
you want to spell that?
Naive Bayes, yeah.
Yeah.
So it's naive as in, well, being naive.
Okay.
That's Naive. And then Bayes is Bayes. And a naive Bayes is based on Bayesian probability. And so that's all fancy words for a layman podcast. So let's try to give you the Bayes theorem, which is just the actual math problem that it's based on, and kind of what it means in layman's terms. So the Bayes theorem is the probability of an event or A given event B is equal to the probability of the event B given the event A multiplied by the probability of A, all divided by the probability of B. That's a lot of words, and especially in a podcast, probably hard to follow. So let's, once again, you're trying to put it into the terms that we've been talking about, and also hopefully terms that are a little bit more easy to understand. So we're trying to figure out the probability of A. So let's say that's the probability of this class. Let's say war, the probability of the class war for a document given a set of features, B, right? Well, how did we figure that out? What is the probability of this category given this feature set? Well, so in Bayes' theorem and in Bayes' probability, that conditional probability, so that probability of A given B is the theorem states that that's equal to the probability of B. So in that case, the probability of these features given that class. So if I know that this class is war and I have these features, that I have that probability, and then I have the probability of just A. What is the probability of that class, right? That's easy. That's easy to write over my data set. Maybe of the 900 documents, 300 are labeled war. Well, there I got my probability of A. That's what the probability in my data set is. So now I can figure out, okay, well, what's the probability of B, my feature set, given that war topic times the probability of just that label over the probability of those features. And once again, you can calculate, okay, what's the probability of the word would? Well, I can calculate that across my data set, count them and divide them by the number of words. Well, there's your probability of that feature, right? And so the probability of that feature given that class times the probability of that class divided by the probability of just that feature is equal to the probability of that topic given those features. And so that's the Bayes theorem, and it goes well beyond just obviously the example of natural language processing that I'm giving, which kind of limiting it obviously, but it's a conditional probability independence theorem that all of these features are independent of each other if I know the probability of the class. So we won't get into some of this probability theory. My professor was he was good with these things, and he wanted us to understand this very well. And so I hope I'm not doing him a disservice here in the way I'm stating it. But probability theory is very important in machine learning, understanding probability and how conditional probability and independence, independent probabilities work. We won't dig any further than we already did just now in that, but a Bayesian classifier does that calculation in order to assign weights to particular features in order to generate that label, right? Because then once I have that model, I know then I have the probability of a particular topic given a set of words, and then obviously it just picks the model just picks the highest probability. Matt, any questions about that? It was how opaque was that?
Adequately unopaque.
Okay. we'll count that. Well, that's pretty good. But yeah, that's a Bayesian classifier, a naive Bayes classifier. Naive, then again, once again, coming from that word being assigned to this because it's naively saying that this conditional probability is independent given the category. Essentially, the probability of this topic is dependent on all these features, but we can say, oh, well, it's actually just dependent on this feature given that topic times the independent probabilities of these features existing in the data. So
moderately opaque.
Yeah, that's what I do. That's what they should probably. My autobiography would probably be titled "Moderately Opaque." A couple other. Let's move away from trying to talk specific theorems and talk a little bit more about just the different models and some of the names that you'd see if you're getting into the machine learning area. We've talked about maximum entropy before. Back in our thermodynamics, we talked about entropy kind of in the physics realm, and that's not exactly the same, but entropy, once again, just disorganization, right? Is that a good?
Yeah, it's the disorderliness of the universe.
Right. And so maximum entropy is a model that essentially says, I want disorder in my model, which is kind of confusing when you first think about it. Because you're like, well, no, if I want a disorder, I would just assign a random probability to everything. But maximum entropy is the idea that I want I want to have my model as least specific to my data set as possible while still achieving the maximum probability that I can, if that makes sense. I don't want to, the problem that you get in a lot of these machine learning scenarios is something called overtraining. So I've got a bunch of labeled data, and then I put my machine learning algorithm to work. I write up the code that does all the feature extraction and all that kind of stuff, and I've got great features, and it learns these models. The model does great on my data set. I mean, it's like a 98% accuracy on my labeled data set, and I'm thinking, wow, I've got this killer machine learning algorithm model here, and I'm going to go and apply it in the wild and see how I do. And I'm going to go get a bunch of other data, and I throw that data at it, and it performs horrendously, just really, really bad. And you wonder to yourself, well, what just happened here? And what usually happens in those types of scenarios is you've got some type of overtraining going on. Your feature set is being so specifically weighted for the data that it's seeing that it can only predict the data that it's already seen, if that makes sense. So
it's basically it's over specialized. It can only recognize the words hammer and airstrike to determine whether or not we're talking home improvement or war.
Right.
And it's not generalized enough to be able to expand and do anything else.
Right, exactly. Because you could imagine a data set where I've got these three topics: war and nature and home improvement, and in my training data, the word hammer only ever appears in home improvement. And so my model says that's a 100% prediction right there. Like I can assign a huge amount of a probability to hammer on that feature set as being able to predict the topic or the class of home improvement. And then I go out in the wild, and then the word hammer is used in lots of war documents, and then all of a sudden my model is doing horrendously, right? And that's this scenario. Is I've got overtrained model that only knows essentially how to predict the data it's already seen, which is useless.
So the question I have on that is that problem an issue of the algorithm or an issue of the data that you fed to it, or both? Like if I want to prevent overtraining, where do I put my effort to prevent that?
Right. The algorithm is the probably the most important there, because you can only do so much with the data. Obviously, you do need to have good data, and you need to have a lot of it in order to train a good model. So it is a bit of both, but a lot of data, a lot of good data can't overcome a bad model.
Okay.
So there's lots of different ways that you can kind of try to deal with this overtraining. But the maximum entropy is one of the most common ways here, at least back when I was in school. And so that's essentially saying, well, okay, we've now assigned all these probabilities. We feel good. Let's back them all off as far as we can, without losing a particular tolerance amount of my training set accuracy. So back off those probabilities on those features. Back them off, back them off, back them off. I want this as disorganized and as possible, while still maintaining a very high level of accuracy on my training data. And now let's apply that in the wild, and that performs significantly better. And so maximum entropy models were all the rage, like I said, like 10, 15 years ago. There are also things, like I said, we talked about naive Bayes. That's still useful in a lot of situations where you've got very simple tasks. Maximum entropy can handle a lot more features, a lot more data, and there's SVM, so that's a support vector machine, and so that's once again obviously a vector. You got a whole slew of features and a bunch of numbers that I'm storing for each feature, and I want to use this whole vector in the right way to predict these classes, and so support vector machines. Hidden Markov models. So that's idea. A Markov model is essentially this class, this hidden class, it exists for every instance of the data, and I need to be able to predict that hidden class. But that hidden class can be is hides the classification inside of it. I'm not doing justice to the specific the theorem here behind hidden Markov models, but the idea once again is just that it's dependent. The probability of this class is dependent on the feature, obviously, but then also usually hidden Markov models also can and the class is dependent on other things as well, like the class of the previous word. So that in this case often used for something called syntax parsing. So if I'm trying to parse a sentence and I'm moving along, and I got the first word is man, right? Okay, well I know that's a noun based on my training data. Move on to the next word. Well, the next word is ambiguous. It's run or something like that. It could be a noun, it could be a verb. Well, now my hidden Markov model is saying, well, let's take that into consideration plus the previous hidden label that we have assigned noun. Okay, well, let's take both of those into consideration, and now I've got another set of probabilities that I can assign to this and better be able to select the correct tag or part of speech for this syntax tree I'm building for a sentence. I think that's the one that I saw the most, at least in my class. Like I said, hidden Markov models are way more than just that. But so these are just a few of the examples of these algorithms and ways to assign probability to these features in order to generate this class or other. It's not just classes. I'm doing classification as an example. That's a very common example in machine learning. There's also machine learning task is also like machine translation. In translation, you're not doing classification, you're doing generation of a new sentence, right? So it's a different task, but using the same types of models. At least it was a long time ago. We won't talk a lot about machine learning here, machine translation. Machine translation is its own whole set of considerations, but machine learning got a lot better. Machine translation got a lot better about 10 years ago when we started using a new model called deep neural nets. And I think this has come up on podcasts in the past as well. Machine translation probably has, because I talk about machine translation a lot. But deep neural nets is once again just another machine learning algorithm and a way to use the features that we have in new and useful ways for very difficult tasks. And you can imagine the idea behind a deep neural net. The idea is deep. You got a lot of dimensionality here. So a lot of different levels of features and ways to assign probability through that. But neural nets being the idea that where I'm going to try to use this in a way that we think neurons work. And I want my probability to walk down a neural net. Like I'm firing up one neuron and that starts exciting the neurons further down that net. And so that probability changes as each neuron starts lighting up given a particular input, right? And so that's this deep neural nets, this methodology of machine learning took machine translation to a whole new level. The quality of translation jumped significantly with using that algorithm. So that's an example of why these algorithms matter and why a particular algorithm can do very, very well. So deep neural nets are I believe still all the rage. They're used in lots of different situations in machine learning. And so that's once again the same type of ideas as features and probabilities, but a different way of using that probability and not training, but tweaking that probability as more data comes in a way that really produces great results. Let's move on from supervised learning and move on to unsupervised learning. Now I have been doing a lot of talking. Matt, anything here that you want to add?
I'm enjoying this educational podcast is all I can add.
Okay. Well, briefly before I talk about
this is not my area of expertise. So
well, you can jump in the end when we're talking about Ray Kurzweil.
Talking about what?
Ray Kurzweil. He's the He's
Oh
known
yeah,
as kind
Ray, my buddy. We
of,
used to hang out.
he's known as kind of being like this. He's made some predictions in the past that have been very accurate about AI and what's going to happen with AI and computers and things like that. And so I believe that he started, well, yeah, some software company. Anyway, he's a smart guy. He's made some predictions that I don't think are going to happen according to the timeline. But who am I? I do learn it from a layman. This guy's, um, like I said, I think he started some major software company, and I'm blanking on it right now. But uh, he's known for having some very accurate predictions in the last 20 years. And so who am I to contradict? I'll give reasons why I don't necessarily would agree with a couple of his predictions right as we wrap up here in 20 minutes or so. But quick aside before I walk us through briefly what unsupervised learning is. Our listeners are still showing up from all over the world, so thank you. I haven't given the due to the UK and India recently. They are going neck and neck for our second country outside of the United States for listeners. So
Nice.
I'd like to see who's going to win this month. My money's on the UK just because they're currently in the lead, but India's got quite the population to draw from. So, Matt, predictions?
May the best country win, and yeah, you can read whatever you want to into that.
Exactly.
No, it's always fun to see where people are listening. So we're just happy that people listen.
Yeah, me too. Though I just updated. India actually is now in the lead.
Oh, so there we go. So now are you favoring them because
they're
winning?
I'm now favoring India. Yes.
Because they're winning. Okay.
Exactly.
Carl is what we call a bandwagon fan.
That's what I do. I've never been to India. I'd like to, but I don't know a lot about the country. The UK I've been to a couple times, and my ancestors, I've got a lot of ancestors from the UK. So I know a little bit more about the UK, but India, now I'm a bigger fan because they listen to our podcast.
Excellent.
I do have to North Dakota once again. I think I called them out in the previous podcast, but they're the one state currently that's not paying attention. So come on, guys.
Well, there's nobody there. Pay attention.
Details.
Anyway, it's all right.
All right. Yes. So one other quick interesting thing. So we get information about countries, obviously, about where our listeners come from. Here, about 2 weeks ago, it showed that all the countries in South America had listened to our podcast. And then all of a sudden, Venezuela dropped off the map. Like, I'm wondering if they just, I know that there are some sketchy things that go on in Venezuela at times.
Well,
so
that's why you insult their country.
Yes, I would apologize.
This wasn't shortly after your podcast on command economies, was it?
Right. I don't know. But apparently we've been shut off in Venezuela, and no longer, they don't even claim to have listened at any point, even though at one point they had. So, all right, back to machine learning, away from our listeners, toward our current listeners, wherever you may be from. Okay, so we've talked about supervised. Once again, that human in the loop. I've got data, I've labeled it, and I've passed it to the computer, and I've said, let's learn a model and let's use that. Unsupervised learning is more magic-esque. It's like I said, my professor called it. This isn't the full dark magic that he said called like chatbots and other AI related things. More just it's using math in a very and probability and those types of things in a very unique way that gives you very interesting data. Uses your data and give you very interesting insights. And so the idea here is that you don't have labeled data. You just have data and features, and you want to learn something from it. So you say, here's some stuff, computer, teach me. and that's unsupervised learning. And so it's not as simple as that, because that's, obviously then you're talking more artificial intelligence. I want to learn a particular thing about this data computer. I don't know labels. I don't know. I've got some features potentially for you. Here it is. Do what you can with it. And so a lot of this is clustering. So it tries to use various methods, and we'll talk about a couple, to take this data and create meaningful groups out of the data. And so once again, a great example is topics for documents. This is one I'm actually by far the most familiar with unsupervised learning is something called topic modeling. And so my first example, the very beginning of the podcast, was I've got these 3 topics and I've got these documents and I've got labels and I want you to learn those, and there you go. This is, I don't know what my topics, in the case of topic modeling, you're saying, I don't know what my topics are and I don't have any data for you to train on. Teach me. And that's what the model. And so in this case, topic modeling goes through and it tries to create meaningful clusters of either documents or words inside the documents that will say, okay, here are some different topics being discussed in these documents. And you have to give it a particular number that you want, or at least back in my day you did. I know there was some work back even then to try to have the computer learn a number of topics that would be coherent. And so, but you say, okay, here I want 10 topics. I want 10 things that are discussed in this document, or in these sets of documents. Go. And so then it goes through and it clusters words, and it creates probability vectors and all these multi-dimensional matrices, and in order to say, okay, there are 10 topics in here that we found. It doesn't label them because computers aren't great at labeling. So essentially what it does, it'll say, here are the top words, the most common words in these topics. And then you'll see that, okay, from these 10,000 documents, I've got the words computer, hardware, software, monitor. You're like, oh, okay, some of these documents are clearly about, computer science or something like that. And then some of the other words will be student, teacher, class, school. And then you can say, oh, okay, well, this is a topic about, about school and classes. And so it will go through and assign the probability to the words and then be able to map those into topics. And then you'll be able to say, okay, from this document set, I know that these things are discussed and these are topics that exist in these documents. So topic modeling is one example of unsupervised learning. Like I said, these are mostly just clustering algorithms where I want to find some meaningful clusters inside my data that will teach me something about my data. And so lots of different ways you could apply this. The topic modeling is just one example. But let's talk about a couple of different ways that they do this. Clustering algorithms, there's something called k-means. Essentially, that's you're using a mean number, so some average of data points in order to calculate a probability of a particular topic. Once again, giving the one example that I've given you here of topic modeling. K-means, there's something called nearest neighbor. In that case, you just use the nearest neighbor or neighbors for a particular data point given the feature set in order to predict a particular outcome, a particular cluster.
Can you define neighbors there? Sorry.
Yeah, so that's the idea. Once again, once again, I didn't ever say what the idea was to begin with. You've got a multi-dimensional space, and that can be really confusing for a layman. It was to me.
Or other people, experts.
Right, exactly. So we're familiar with 3 dimensions.
Really, only the machines can handle that.
Well, you can just multi-dimensional space is it's easy to imagine if you can imagine the each word is a dimension. And so That's, once again, all of my examples are coming from natural language processing. So,
Right.
sorry, make your generalizations however you want to. But
Anyway, neighbors.
yeah, each word is a feature. And so each neighbor is a document, and each document has its own set of dimensions in it. And so these dimensions, being all these words, are how close is this data point to this other data point given all its dimensions. So it maps it in, and it can say, oh, okay, it's very close to each other. Therefore, they're neighbors, meaning lots of these dimensions overlap and share either qualitative or quantitative. Well, qualitative, obviously, in this case, feature similarities. So quantitative, sorry, not qualitative. Okay,
I was going to say, but that's fine. So basically, based on the multidimensional analysis that the computers or the algorithm does, if a thing is similar to another thing and its features overlap, then they could be considered neighbors.
Right, and the nearest one is the one that has the most overlap in features.
Yeah.
And multidimensional is just literally a big matrix of the features, and each one, in the case of words, they all take on particular, there or not values, right? But you can imagine if I've got other values like words, like pixel colors and things like that, all of a sudden you can imagine how that maps into space differently. Anyway, nearest neighbor, and then the one I was talking about, topic modeling, we usually use something called latent Dirichlet allocation, or LDA. Dirichlet is just a fancy word for a particular statistical probability model. So a Dirichlet is a multi-peaked surface. You can imagine you put a sheet and then you stick like 10 different poles up underneath the sheet, and they get, so your sheet, which was flat, all of a sudden has 10 spikes coming up through it. That's kind of what a Dirichlet looks like. Different areas where it's spiky.
So if you basically drape a bed sheet over the head of a deer, then the antlers would creep.
There you go.
Never mind.
And so you can imagine, yeah, well, that's reasonable. So you can imagine I've got all these documents, and different documents have different topics in them, and I want to find where each document has these different topics and what the topics are, and some topics are going to happen more often, and so that's your more spiky parts of your plane here of probability.
When we talk about spikes, we talk about points of increased probability.
Right, exactly. And so the and two important things here. There's some these two words that happen a lot in probability theory, and also then in machine learning, is a prior statistical probability and a posterior statistical probability. So your prior is, I either have no idea what the probability of this is, so 50% or whatever, versus my posterior, meaning I've gone through and I've updated my probability of this feature or this document happening.
It's a known probability distribution.
Right, exactly. Posterior meaning I've done something and now I know something about it, and right, the probability has now changed. So prior meaning before, posterior after, and so that's how you start. There's lots of different sampling methods that you go through in order to create these probability assignments for the different features. One I'm familiar with is called Gibbs Sampling, where you go through and it uses calculus derivatives in order to figure out what a feature adds to a particular document and what the probability is with and without, and it goes through massive amounts of calculation in order to do a big topic model for a data set. And so I think you started seeing this in Google relatively, I don't know, last 5-6 years. I think they do a little bit of latent Dirichlet allocation. They do a little bit of topic modeling, I think. I don't know this for a fact, but I do know that, let's say you type the word Bryce Harper. For all of our listeners who have no idea who Bryce Harper is, he's a baseball star in the United States. He plays for the Philadelphia Phillies, okay? So you type in...
I didn't know who he was either.
Okay, well, so you type in Bryce Harper and it comes up with results, right? and now you go back and you start typing something else. I guess there's two ways to look at how they might use topic modeling. First of all, before we move on to what your next search might be, your first search, you're going to see that, and then you're going to see related people, right? You've seen that in Google before, where you search a person and then it says, oh, all of these people are related. That's going to maybe not be topic modeling, and maybe they use latent Dirichlet allocation and maybe not, but it's some type of clustering algorithm, right? Because it's not like they've gone through and labeled how these people are related, right? Nobody has done that. There's billions of people in the world, even famous people. There are millions of people in the world, so you can't do that. But computers can with a particular amount of data, and Google has vast amounts of data and a lot of computing power. So Google has, I believe, found some ways to use latent Dirichlet allocation, which for a long time really wasn't all that useful real time because it takes so long to train the models. I think they've found a way to use it, and maybe they use some pre-trained models in some cases, but those clusters of people or related topics that you see when you do a search in Google, I believe, come from some unsupervised learning, where it's grabbing ideas and things from these vast data sets that it has and associating them together in a cluster. The other thing is when you type, after I type Bryce Harper, I've read something, and I go up there and I start typing PHI. That could go anywhere, right? PHI, there's a lot of, well, this isn't a great example.
Go to Philadelphia because Bryce Harper plays for the Phillies, which is
right.
Why you would be typing that, right?
Right, and that's, so Google, the first suggestion will come up with Philadelphia Phillies.
Mm-hmm.
And the reason that it is the first suggestion is because it's the most tightly, it's the nearest neighbor, right? So it is clearly done, it's starting to predict your next search based on your last search, based on these unsupervised clusters that it's created. And so that's why unsupervised learning is really cool, is because no human is in the loop there. There's no label that's going on here. They've just created these meaningful clusters that are now useful. Because I searched Bryce Harper and I learned, what are the Philadelphia Phillies up to these days anyway? So I start typing and it's already filled that out for me, and I can pull that up really quick. So that's an example of how unsupervised learning might be used and what you'd see day to day. So we talked about unsupervised and supervised learning. Like I said, I talk about them in the natural language processing or NLP area. These are used across. Matt used the images are a huge one, right? Google Photos, if you haven't used that, or Amazon Photos, you can type in grass. Go to Google Photos right now, type in the word grass in your Google Photos, and you'll see that Google pulls up all your pictures that have grass in them. Pretty cool, right? It's not like anyone did that. It's they had models that know that, oh, here's a bunch of green. What does green mean? Oh, well, it means grass. So that's an example of how machine learning has been used in other areas outside of text as well. Questions, Matt?
Yeah, I think the ultimate question for everyone that's listening to this podcast is, how much longer does humanity have before the machines do take over and decide that? Do you want to talk about like some of the sci-fi depictions, kind of a myth versus reality as far as some of these AI considerations and machine learning goes? At the end of the day, no, the machines are not going to take over. But you want to talk about that a little bit?
Yeah. So we are, I believe, quite a ways away from these self-aware computers and those types of things. Most of what's still being done out there is more in the realm of task-based machine learning. So very specific jobs that computers can do very well. Now, that's been the case for the last probably 15 years, and so we really are at the cutting edge, which I'm not at, obviously. We are starting to see some combination and some more AI related things, where you actually get some interaction. The Turing test is one that you can look up if you are interested in how when we're going to decide we're at this point where the computers are all going to take over. Alan Turing lived back in the early 20th century, and he was a mathematician, computer scientist, and he said when computers are able to essentially carry on a conversation with a human, and you don't know that it's a computer, that's when we've reached this level of AI that's the point where it could take over for a human, essentially. Like I said, right now that's not the case, right? There's so many things that we interact with on a day-to-day level, and the biology of humans is uniquely set up to handle, obviously, the society that we've created for ourselves. So it makes sense that we'd be really good at handling the things that we have set up as a civilization. Computers are learning, but learning in the way that we've talked about, with data and numbers and things like that, as opposed to more the biological idea of learning that we're more familiar with. So it's a very different take on it, with the exception of cognitive modeling, which still is different. But let me I mentioned I would talk about cognitive modeling, and we're low on time here as far as people's interest potentially even. But cognitive modeling is the idea that, once again, in a particular circumstance, put me in a car, give me a phone and a burger, and have me drive, right? Things are going to go poorly, right? If I'm trying to text and eat and drive, I've used up too many of my cognitive resources to be able to do any one of them particularly well. And so there's going to be issues. And then that's a very simple case of walking and chewing gum, right? You're using more than just your basic one task cognition abilities. So when you're trying to do multiple things at the same time, your cognitive ability is being put to use in two different areas, and therefore they suffer, right? There's a certain amount of neurons available to you, and if you use them up, you've used them up. And so the idea with cognitive modeling is, okay, well, we know computers don't have the same limitations as humans do in a lot of cases, but we want to know what humans' limitations are, and we want computers to be able to mimic that, both for the sake of creating human-like computers, and also for the sake of being able to say, well, what happens when you put a human in these very stressful situations, right? If you a pilot that's flying 500 miles an hour and then all of a sudden has a woman giving birth on the plane, and then an engine goes out or something like that, incredibly stressful situation. And how is that human going to react? And can we figure out what ways we could help that human based on a computer model? And so a computer cognitive model is a different architectures that cognitive model program set up to try to give you the idea to mimic a human reaction in particular situations. And I got a certain number of, and I'm familiar with the one that used at the University of Michigan for a long time, the SOAR architecture. And they use something called operators, and that's kind of like a decision-making neuron. And you only have a certain number of operators, and it has a particular, and then this architecture has different goals for the program. So there are different things that it has to do, and when you give it different goals, the amount of time that it takes to do these different things then changes. So that you can imagine that obviously you're now starting to get some insight into, if I can correctly model things that I have seen from a human, then I can take this model and this cognitive model and apply it to new situations, and you can imagine that a human's going to act like that, probably, right? And that's cognitive modeling. Once again, I'm familiar with in the language space. How well can we model how a human parses a sentence? So if I'm talking in the past, I don't remember which podcast it was, we talked about garden path sentences where you start parsing, you're listening to me talk, everything's making sense, then all of a sudden I say something and the sentence blows up in your mind, like the horse raced past the barn fell. And you're like, what is he what? And that's a garden path sentence because you've gone down and all of a sudden, pop, the way that you were structuring the sentence doesn't work. You got to go all the way back up and try to see if you can figure out a different syntax tree for the words that I just gave you to have them make sense. So in a cognitive model sense, in parsing, you want it to do something similar, right? You want to be able to give it a garden path sentence and have it fail and then recover. And or in the case of some garden path sentences, even humans don't recover. You want the computer to say, nope, can't figure that out. And you want it to be able to parse a sentence in about as long as a human takes to parse a sentence, which in the case of human speech is real time. But if I'm given then another goal at the same time, you need to listen to this person and you need to drive, then I want to see that how those play off of each other, right? What is the interaction there? If I'm listening to someone and I'm driving, is my driving impaired or is my listening impaired, or are they both impaired? And so cognitive modeling is very useful in that way as well. So that's just a very basic into cognitive modeling. Like if you take it all the way back to Matt's question, the computers are they are not yet self-aware, and I don't believe that we're close to being self-aware. I don't think that's even something that makes sense for a computer, candidly. And that's where I start diverging a little bit from Mr. Kurzweil. Ray Kurzweil, by the way, I did do some research on him. His wiki says he's an author, entrepreneur, futurist, and inventor. And I believe he was one of the early people in Google, which makes sense, which is why I thought he started some big software company.
Glad we're able to check these things in real time as we go along here.
Anyway, like I said, lots of predictions. He's done lots of amazing work. But I believe is some of the predictions he's got for humans and computers are that, let me see, 2008, Kurzweil said that solar power will scale up to produce all the energy needs of Earth's people in 20 years. That's a simple one. He's got ones essentially that, the humans will be a hybrid of biological and non-biological intelligence by 2029.
Interesting. Well, I think we're starting to see some of that with TikTok.
Right. So I don't think that's going to happen. I think in some ways it's because we as a biological creature are allergic to the idea of being partially AI, right? I think the ability isn't quite there yet either. We're made a lot of advances into being able to read brain waves and understand the brain, but it's still a bit of an enigma to us, at least how all the cognitive functions work, and consciousness in general is still kind of a question mark in a lot of ways. So Kurzweil kind of assumes that all of that will be figured out in the next 10 to 20 years. I don't know that I agree. And in as much as there's computers are not conscious, they won't be able to do a lot of human tasks. But a lot of jobs don't really need you to be conscious. And so there is, and as there already is, a huge market for computers and AI taking over a segment of tasks and jobs that are very machine learnable. So it's the interplay of multiple things happening at the same time where computers don't do as well. A particular job, one specific job, are what computers are good at. And so that's why learn it from a layman's very important. You need to know lots of different things in order to ensure your job doesn't get outmoded or
replaced by computers.
Exactly.
Yeah.
So you need to broaden your horizons and learn lots of different things so that when the computer jumps in and starts taking your job over, you can say, well, I don't just know how to do that. I can then also help this computer that's now doing my job. I can help it interface with this over here as well, and that will allow our company to do such and such. So I think that's the hopeful side of computer machine learning and artificial intelligence. Is it's not necessarily going to make us as humans no longer necessary. It's going to allow us to do new and innovative things. And I think the Kurzweil's idea of biological, and it's not just Kurzweil, but biological and computer interaction. So essentially, we're going to have little nanobots inside of us, and we can use them to access data on the web inside of our brain. That sounds really cool, and maybe eventually we will. I think we're a long ways away from that. And I don't know that we'll get there in the same way that he envisions it, just because I believe that as a species we're a bit hesitant to walk down that road. But I do think that in the very positive sense, AI and computer machine learning will give us, and already have given us, a lot of ability to do new things and view new horizons. So that's pretty much my summation here.
I agree with your summation.
Last questions or ideas, Matt?
No, I think you've pretty much covered everything that we need to know about machine learning and AI.
Good. Well, then we can't do another podcast about it, Matt. I think there's a lot more to cover here. Anyway, no, I hope this has been useful. I hope that we try to be very factual and learn it from a layman. We try to be well educated. We're not always perfect, and we know that. We've had some feedback about our podcast, and we appreciate any feedback you can give us. We try to do our best, and we will try again next podcast and come back for our next one. We'll see you then.